pick 4 points and draw the tangents. Then I gotta rename stuff. Oh well. So this will be A, B, C, and D. And we can call those E, F, G, and H. E, F, G, H. All right, so those 4 are the lines from A parallel to IC, B to IB, so on. Okay. Let me just make these sides instead for now. All right. So we have this parallel, B to IB, C to IA, and B to IB. They form this quadrilateral right here, and then PQ. Let's make it look a little nicer. Okay, so maybe like this. So I don't know what M, N, P, and Q are, but it doesn't really matter. And the diagonals intersect at S. Okay. All right. So we have this, 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 and this. N, P, Q. And MP, so those intersect at S. And then take the midpoint of IS. And we want to show its intersection. So we want to show it lies on both BD and AC. Okay. Is that quadrilateral cyclic? Let's see. That makes it look like, okay, I just guessed. I guess I was lucky. So that's probably just an angle chase. just because, yeah, you have all the parallel lines. So, yeah, it's the same. It's because angle BIC plus angle AIB is 180. That makes sense because, yeah, BIC is BIF plus CIF and so on. Okay, so you have a cyclic quad. But I don't think this is a right angle. I'd be very surprised if it was. Yeah, it's not. Okay. So what does Newton's theorem say? I forget. So maybe J also. Yeah, so Newton's theorem, I guess, says that these all concur. I think that's what Newton's theorem is, right? That EG, FH, and the diagonals concur. Or maybe that's not Newton's theorem, but that's a true fact in general. Okay. So, I mean, we could show that instead if we really wanted. Just delete those for now. So I wonder if FEHG is similar to QPJM. It doesn't seem like that should be that hard to check. So this angle, yeah, I think it's true. So I think we might be able to show those quadrilaterals are okay. And then if those quadrilaterals are similar, then FH and EG, like it's almost like a homothety. So S and J would correspond. Just have to use that as the midpoint. Yeah, two similar quadrilaterals, and S and J correspond. But it's not like one's homothetic to the other. Maybe, let's see. So if I do QH, ME, PG, and JF, do those concur at a point? Yeah, maybe one of them I drew wrong. It kind of looks like it, but I don't know. And I'm not sure exactly what that would do. I guess that point would have to lie on IS. So yeah, so let's see if I drew everything right. FN, QH, ME and PG. Yeah, I'm not sure. Maybe it needs to be EP and GM instead. I'm not 100% sure. Because what do we want to show? Okay, so Stefan's, yeah, I have no idea if we're on the right track or we're way off, but yeah, Stefan's probably just watching us like, yeah, anxious.
No, I'm trying P3 right now.
Okay. Let's see. So F corresponds to N and H corresponds to Q, but let's see. Let's try this and this. Okay. So E and P, that's kind of weird. Okay, so I think E and P correspond and G and M correspond. And then let me just draw all the angles then. So, oops. F. Whoops. Okay. See, that's interesting because F corresponds to N, but E corresponds to P. Yeah, I don't even know if these are, I think they have to be similar. Yeah. But if they're similar, then I would think there should be a center of homothety. I'm kind of confused why that's not the case. So EP and GM and
I just want to say that I actually have progress in the last problem.
oh, you solved it?
No, but I proved one of the two lemmas.
Okay. Let's see.
The one which is left is the concurrency one.
Okay.
So I proved that this thing with locus. It actually isn't. I mean, I didn't have any. The proof wasn't difficult, so it is a bit strange. So what I did: intersect BJ with AS.
Okay.
We will. We will define everything as in the problem statement.
Okay.
So we have that point J. We define it like as the reflection of B in the bisector of angle AGD. Basically, like you have that symmetry, and we want to show that the JKA is that circle is tangent to both of those lines.
You mean JKB?
Yeah, JKB. Yeah.
Okay.
In order to do that, we would have that AJB is JKB. That would be equivalent by
Right.
angles. And what did I do?
So AJB is JBC also, right?
Yeah. Let me see just for a second.
Right.
I saw that that is equivalent to proving AJKM is cyclic, but not seeing it right now exactly how it is equivalent.
AJKM.
Yeah.
Let's think about it.
No, I can't remember how I got that.
Okay.
So let's say it is equivalent.
Yeah.
And then intersect KB with AD. Just because J isn't precise, that's why it doesn't look like that intersection lies in the circle, but in fact it does.
Okay. All right. So there we go. All right.
Okay. So we could prove that MN is parallel to BC, and that is, I think, by a homothety or something like that.
Okay.
And because of that, we have that AMN is ASD, which is equal to AKB.
Okay.
So basically, we know that AKMN is cyclic.
Okay.
And there was some symmetry, like, which proved that AJMN is cyclic also. Let me just see that for a second. Yeah, that is quite obvious. You just have that angle ANM is ADV, and you have that JBTA is like an isosceles trapezoid, and yeah. So basically, we have that AMKJ is cyclic.
Yeah.
And
then it's easy to see that this circle's tangent to both.
I think, but I don't see it right now, how it is equivalent.
So that's just the same as showing that JKB is equal to JBS, but JKB is JKN is JMN, which is JBS.
Yeah, that looks good.
Okay, so
I hope that I didn't make a mistake.
Yeah, that we didn't use circular.
Yeah.
Okay,
Let me just see how we have that MN is parallel.
Oh yeah, that's true. We have to show that.
That is like the main part, I think. So we want to show that AD over AN is AS over AM, and AS over AM is AF over AB, and that is true because we have FD is parallel to BN.
Yeah.
So I think this is true. This is all right. What I did.
Okay. All right. So
it is left to show that KL and BC and that perpendicular bisector concur.
Okay. Did you say KL?
That is the other point.
This one.
Yeah. The concurrency is left.
Okay. All right. So what we did so far, we proved that circle's tangent, right? But then we thought by inversion that maybe that would solve it. I'm not sure.
Yeah, but we needed the collinearity in order to use that inversion. I mean, we can invert, and those two circles indeed invert to each other, but in order to prove that KBCL is cyclic, we need to show that K inverts to L, and that we can do that just if K and L and G are collinear.
Okay, so I'm going to write what we have so far. So let J be the reflection of B over the perpendicular bisector of AB. So yeah, let's check that we didn't make any mistakes. So B over the perp bisector of CD. Let AJ meet BD at G. Okay. And let AS meet BJ at M. And let AD meet BK at N. Okay, so the first step, so we want to show those all lie in a circle. Trying to remember how this goes.
We prove that AJMN is cyclic and that AKMN is cyclic.
Okay, so for AKMN.
But first we prove that MN is parallel to BC.
Okay, so first we prove that MN is parallel to BC because AS over SM is AF over FB, which is AD over DN. So that kind of proves it, right?
Yeah.
So AS over SM is equal to AF over FB because we have that parallel. So we have two parallels. So SF, yeah, S over SM is AF over FB is AD over DN. So yeah, it's equivalent to a homothety. BD is parallel to MN. And that means that then it's clear that AJMN is an isosceles trapezoid, so it's cyclic. So AJBD is an isosceles trapezoid. So AJMN is also, and thus cyclic. And then for AJ, for AJKN, that was the other one, right? Let me remember how to do that. So yeah, how did you show AJKN was cyclic?
Angle AKN is ASD, which is AMN.
AKN is ASD, which is AMN. Ah, good point. So then we have AJKMN is cyclic. And then from there, angle JKB, angle JKB is JKN. Yeah. Which is JMN, which is JBD. That means that the circle JKB is tangent to BC. Okay. So yeah, if we can show that K, L, and G are collinear, then that solves it. But I wonder, because, okay, suppose we try to invert. So K is defined as the intersection of these two circles, but what if we inverted this circle? Yeah, I guess it's kind of hard to invert that. But yeah, that's some good progress, at least. Let's look at this for another couple minutes. Okay, so we draw the perpendicular bisector, maybe. And we reflect C over it. That's C prime. Well, that doesn't do that much, really. Let's draw CL. And yeah, maybe we could even do Ryan's idea of letting these intersect at a point. I don't like the O. Let's be careful. Let's call this X. Yeah, maybe there's something else special. Let's see. So that circle's tangent. And let's draw C prime. The circle should also be tangent, CRL. Okay, so it's like K and L, we want to show are kind of like anti-homothetic. Or, I don't know, I think there's like a word for it. What do they call it? Anti-homologous or something? Okay, so I'm going to hide this line just so we don't get confused. See if this works. Centers. So BK is parallel to DF. CL is parallel to DE, and then from there we have to show those are collinear. So is there some homothety that takes, because this is parallel to this and this is parallel to this, that kind of makes me think of homotheties, but I'm not sure. Maybe we could even use Bonge's theorem somehow, but I don't think that would be that easy. So I wonder if we could kind of do it like this. What if we try to use trig-Cheva and we try to find sine JGK over sine KGB in terms of the sines of these angles. And basically we try to show that that ratio, sine JGK over sine KGB, is equal to sine RGL over sine LGC. Like, yeah, that's just a thought I had.
Yeah, this may be best.
The way that I just said.
I mean, I don't know, but yeah, it looks fairly okay.
So like the sine of this over the sine of this, like since this is tangent, angle GJK is angle KBJ.
Look, you have a trig Java in GBJ, that
GBJ.
triangle. So I will not tell signs, but angle BGK over KGJ, sines of those two, that is equal to GJK over KJB times JBK over KBG.
Yeah.
Oh, actually, you multiply all those three and you get one.
Yeah.
So you have those tangents. So I think you will get something like KBJ over KJB, sines of those two, and then squared.
Okay.
And you can use sine rule of sines in KBJ to get that will be equal to something like KB over KJ whole thing squared, or the other way around. Don't know now.
Okay.
And that will actually mean you want to prove that KB over KJ is CL over LR.
Yeah. Okay.
Right? Or something like that. So are those two like similar? They're almost similar, right?
Here's the thing. So that ratio would be true, like by a homothety, JK over KB equals RU over UC, right?
Yeah.
So that would be true for this point, but not this one, if that makes sense.
But it is still true, but you just have like a harmonic bundle.
Oh yeah, it's a harmonic quadrilateral. Yeah.
Yeah.
Okay.
So like those two triangles are the separate parts which form harmonic quadrilateral.
Yeah.
I mean, that is not exactly true, but yeah.
So maybe that doesn't really make the problem any easier, because maybe it's just going in circles. I don't know.
No, I think it is all right, since you want to find the ratio KB over KJ. You know.
Yeah, and we know that ratio is RU over UC, right?
I think U is unnecessary. It just complicates stuff.
Okay.
Yeah, but I think this is really good now, since there was, when I was doing this problem, at the time of the competition, I think I found one similar triangle with JKB.
Okay.
So.
Well, BMN is similar to it.
Not that one.
Okay.
Something from triangle ABC and those points in there.
Okay.
That is probably very easy to find by some experimentation.
All right.
Yeah, I think it is triangle FSD.
FSD.
Yeah.
Interesting.
Just check the angles.
Yeah.
But I think it is fairly easy to prove, since now we know the tangency.
Yeah.
Yeah, that angle can be angle traced. And
but it says 107.84 versus 107.7.
That is
J isn't perfect. That's why.
Yeah.
Okay.
So, yeah, I think this is really good now.
All right. Yeah, J is not perfect. That's the thing. Oh, but that's okay. So basically, yeah.
Okay, this is really good now. So we want to show that Kj over Kb is Lr over Lc, and we have those two similarities. We have an analogous similarity with LRC. So we basically get rid of everything outside of triangle ABC right now.
Yeah. So yeah, I mean, we just want to show that ds over dt is fs over et, right?
Exactly, and that looks very easy.
And ds over dt, so fs over et is fs over ad times ad over et, which is bs over bd. Yeah, it looks very easy, right?
Yeah, I think that is pretty much trivial.
Okay. How let's see. Can you see, do you see right now why that's true? It looks really easy. I agree.
Yeah.
Why is it true?
I think that if we just write things down, that it will come.
Oh,
naturally.
so is SC equal to BT? I think
No.
it's
No.
Well, because what I was thinking is FS over ET is FS over PD times PD over ET, and FS over PD is CS. Okay.
So here, for proving this, I'm pretty sure we will either use Java, the standard Java, or one OIBL, which is both are very easy.
Okay.
Okay, let me just write this so
Yeah.
to check if this is really that easy.
But yeah, it seems like I agree. It has to be like bashable. Yeah, I think let's see. Yeah, once you know those triangles are similar. Yeah, Fs over Et is Ht. It's Hs over Ht. So it's the same as showing Hs over Ht is Sd over dt. And that's the same as showing those are harmonic.
Oh, we need to prove that Ft and Se intersect on AD. That is equivalent.
Oh, you know what? Actually, I think it's easy. So here's my proof. So FUEH is harmonic, right? So if we take FUE and H, which is harmonic, and we just take the parallels to BC, then STDH is harmonic, right?
Yeah, I see.
Yeah, and I think that solves it.
Yeah. So we solved the problem.
Yeah. Should I type it up or just move on to the next one?
Let's type it up.
Okay.
I think for this part, the key step was you mentioning trig Java.
Okay. So, all right. So FEUH is harmonic. And that means that STDH is harmonic. So, okay, so first I'll write by an angle chase JKB is similar to FSD. And RLC is similar to ETB. So we have STDH is harmonic, and that means that SD over DT equals HS over SD over DT equals HT over HS. Which is HE over HF. So sorry, I flipped this around. It should be HS over HT. Which is HF over HE. Which is SF over ET. And then that so that means that JK over KB is RL over LC. C. Well, so I guess I could do it like this. So so that would be the same as RV over VC. Well, oh, but we don't know that they're. I guess I could just let it. Like I could just say define V this way. So then we do have a homothety. So RV over VC equals JK over KB equals RL over LC. This is like that. So that implies that RVCL is harmonic. So yeah, I guess we can skip the trig Cheva just by doing this, right? And then, so that implies that GK and L are collinear. And then by a homothety at G, or by inversion at G. What was the idea? Once we know that those are collinear, then
the idea was that inversion at G, we read is GB times GC, the square root of that.
Yeah.
Swaps those two tangent circles. And since K and L are collinear, and I mean, it is like obvious that they're not homothetic. Like you, you get that K and L swap, and that means KBCL are cyclic.
When an inversion at G swaps JKB and RLC. That means that KBCL is cyclic. All right, very nice. So let's see if we have time. Let's see, we have like 23 minutes left, which isn't a ton. You want to do a really easy problem, or just see if we can solve it? Or you've already done it, right? But is this a really easy one?
It is a middle of difficulty, not too hard. I mean, not hard at all, like the last one which we just solved. But yeah, it is easier than that one.
This one?
Yeah.
This one is harder. The solution of this one? Just go through it, or?
Okay, I mean, I can. Let me just think about it for a second. Okay. So you complete the quadrilateral MNPQ. So you draw in the intersections of opposite sides and that, yeah.
Interesting. I probably would not have done that.
And then one thing to observe, yeah, is that, for example, BLDI is a parallelogram. That is quite obvious, just because of the parallel lines.
Okay, BLDI. Yeah, yeah.
So IL bisects BD.
Okay.
And also similarly, IK bisects CA.
Okay.
So there is this one theorem called Anne's theorem, which I didn't know the name of, but I just asked the moderator if I could use that theorem. I didn't know the name, and he said, "Oh, you can use it. It is called Anne's theorem."
Yeah.
So it is called Anne's theorem, which says that if you have a point, it lies on the Gauss line of the quadrilateral, if and only if it
The area
halves the
AID, the area AID is equal to area BIC, right?
Yeah.
Yeah.
No, but that sum is half of the area of quadrilateral. I actually saw that theorem on your video of the Gauss line.
Okay.
That was the first time I saw it. So that is a very easy way to prove that I lies on the Gauss line of the quadrilateral, which actually means that KIL are collinear.
Okay, because K and L, because K is the midpoint. So you could show area BKC plus AKD is half of the quadrilateral.
No, you don't have to do that. You just.
But I lies on the Gauss line. I agree
Yeah.
with that.
I lies on the Gauss line, and K and L are just the reflections of I in the midpoints of BD and CA.
Okay.
So it is quite obvious that they are parallel. They are collinear, yeah.
Okay.
So drawing those two diagonals, BD and CA, and intersect them with KL.
Okay. KL.
It may be surprising, but we are almost done.
Okay.
And that was surprising to me when I solved the problem. We want to show that I, J, and S are collinear. So let me just think for a second. Yeah, we would want to show that JR, or rather BD, is parallel. Let J be the intersection of diagonals. Okay. Then we would want to have a homothety at I, which sends triangle OJR to SKL.
Okay.
So since we already know those two midpoints with O and R, we will want to show that, for example, JR is parallel to SL.
Ricard's. Yeah.
Is it Ricard's theorem?
I think it might be.
I mean, I just did one projection and that was it, but don't see Ricard's theorem. Exactly.
Okay, yeah, I was just guessing, but
yeah, I basically just intersected QN with KL.
Okay.
And then you project through L and project the cross ratio QNST, which is -1, and you project it onto line BD, and you get that SL is parallel to BD very easily, since R is midpoint of BD.
Okay, so if I write out a sketch, by Ann's theorem, see my video on the Gauss line. I, K, and L are I, R, and O are collinear, or R and O are the midpoints of the diagonals. BL by an angle chase BLDI is a parallelogram. And then so is CKAI. Actually, I'll just say by the parallel lines. It's not even really an angle chase. Okay. So so that implies IK and L are collinear. Okay. And then so we want to show a homothety. We want to show LS is parallel to RJ. And you got that by projecting, sorry, so did you project through N?
Through L.
Through L.
Onto BD.
Projecting through L onto BD. BD. We find we want to show LS is parallel to BD, and okay, so so QNST we find LS is parallel to RJ. Similarly, KS is parallel to OJ. So then a homothety at I with ratio 2 takes OJR to KSJ. OJR to KSL. And that proves it. Implies the midpoint of IS is J. All right, that's it. That's an interesting one. So yeah, you just got to see those parallelograms and then use Ann's theorem. It's creative. All right, let's see. Let's just take a look at this problem quickly. It looks simple, but I guess maybe it's harder than it looks. I'm having trouble maximizing.
It's not too hard.
Okay. Why am I having so much trouble maximizing? Come on. Maybe that'll fix it. There we go. So you have the 3 altitudes, A, B, B, E, C, F. And we draw parallelograms. D, E, F, and out. Orthocenter. So BDFU is a parallelogram in CDEV. I'm going to do it like this. This looks kind of familiar. And UV and EF intersect at X. Okay. And okay. I'll hide these for now.
You drew in wrongly, U and V.
BD. Oh, you're right. Dang it. Okay, so I need the midpoints of BF and CE. All right. V. Delete this guy. And then UV and EF meet at X. And we want to show DX is perpendicular to UV. That's pretty interesting. Okay. B, C, D, E, B. Let's make it look nicer. But yeah. Okay. Oops. All right. I'm going to draw the midpoint of BC. So the GI and GJ are perpendicular. Okay, so we want to show DX is perpendicular. So this DH is an angle bisector. How should I do this? Looks like, I wonder if FXU is similar to EVX. I'm not positive on that, but, well, that would be the same as saying that EB and UF are parallel. Let's check that. Don't know that, well, yeah, that's true. Yeah, so those are similar triangles. EVX and UFX. So UX over XV is UF over EV, which is BD over DC. Okay, so that's interesting. UX over XV is BD over DC. So I wonder if we extend UB and CV to meet at a point. Basically, then that point should be collinear with D and X. So we have to prove that. Let's see. Okay, so if we show XD and K are collinear, no, that's not true though. So let's see where I went wrong. ux over xb is uf over ev, which is bb over dc. Oh, I guess it just doesn't work like that. Like, but I feel like that's progress. We also know that fx over xe is equal to bb over dc. So, I mean, it's a lot of information. So if we know that.
Okay, since we don't have much time, I will give one hint for this problem.
Okay.
Prove that XH is perpendicular to EF.
To what?
EF.
Yeah. Okay. So H is the in center. So that's like saying that that's the in circle, the foot of the in circle. So maybe we could let X be the foot of the in circle. And then we want to show that U, X, and V are collinear. And that might just be ratios. Because if we could show that XF over FU is XE over EV, then that would solve it. Which is the same. So XF is FK and XE is EL. So that's the same as saying FK over BD is EL over CD. And is that obvious? I'm not sure. That's the same as, it's also the same as saying that these triangles are similar.
Delete the incircle.
Okay, delete the incircle. All right. Why would those be perpendicular? So maybe it's just similar triangles. So BD over DC. Maybe if I let XH meet it at this point, maybe. No, I don't think that does much. So I guess another way to think about it is it's the same as saying HX is parallel to, we draw the midpoint here. HX is parallel to GK, but I'm not sure. How do you prove that?
UF is BD.
UF equals BD.
Yeah. So what is UF over EV?
So yeah, UF over EV is BD over DC.
And HD is perpendicular to BC.
Okay. Oh, because these triangles are similar right here, HFE and HBC.
Yeah.
Okay. So yeah.
Okay, since we don't have much time, I will just say that the finishing thing of this problem is to prove that then since you want to show that UXD is 90, and you have that FXH is 90, you want to show that UXF is similar to DXH.
UXF is similar to DXH.
Yeah,
Okay.
that is not hard to do, and I think that just finishes the problem. Then.
Okay. Interesting. Because, okay, so if we know that those are perpendicular, yeah, you want to show that angle, yeah, DXH is UXF, and you could do that by trying to show those are similar, and that is probably not that hard, I guess, because then you want to show UF over FX is HD over HX, and that's probably just like a calculation, because all those look calculatable, because UF is BD and FX, like this triangle similar to this, so yeah, then it's just ratios from there. All right, yeah, or what?
Not even a calculation, you just have directly that those are similar. You see that FXH and the BDH are similar.
Oh.
Yeah, and then just one angle chase finishes that. You have to show that XHD is XFU. Those just, you have one angle, and yeah, that part is really easy.
Okay, yeah. Actually, I think that's equivalent to what I was thinking. But yeah, once you know FXH and BHD are similar, then since BD equals FU, then it shows that those are similar. And so then, yeah, spiral similarity does it. All right, that was a fun finish. All right, so I'm going to stop here. So for everyone watching on YouTube, thanks for watching. And I want to thank all the participants on the session. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. That's in the description of my video. And we meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.